classes here. They did some demos. I hope you got a chance to see that. So our lab's main interest is to understand why most of the modern robots cannot behave like living beings like this. For example, if you can see this cheetah running very fast, and obviously we know that the signals from the pores doesn't have enough time to go to the brain and then compute there and then come back to the muscles at the speed of this running. It has to be stabilized with some other dynamic mechanism. And then this mountain goat climbing up this steep dam surface, and if it slips, there's no time for the brain to react. So it's impossible. Like, to give you a ballpark figure, a signal coming from my fingertip will take about 120 milliseconds to reach my brain. It reaches the spinal cord within about 15 milliseconds. And if the pain signal is too high, it will take a short circuit through the spinal cord. And then make a very, very crude decision to the muscles to take the hand away within about 15 minutes, 30 millisecond complete cycle, and then it's completely subconscious. You can hit somebody here because you're not thinking. So if it goes to the cortex, it takes about 300 milliseconds to come back, and then it doesn't have enough time to survive like that. You can see these goats climbing up the branches to relax. And then we can run across different terrain conditions without losing stability. And none of the robots we know of today cannot do any of these things after more than 50 years of control theory. Mechanical engineering, we have advanced so much, but we are missing something. That is what we are trying to understand. What is missing? For example, give a simple example, like we can hold a hamster. A gentle thing like that. Can you trust a robot to hold a hamster like that? You don't trust a robot, right? But I mean, after about 50 years of mechanical engineering and control theory, we cannot do this. Something very subtle must be missing. So that is what we are trying to understand in my lab. So the robotics has a long history. It started as a political movement. In 1920s, the first artist called Karl Kopek, he came up with a stage drama. He got humans to behave like workers or machines. He called them robots. The closest word in Czech language to worker is robot. So he put that name to kind of forced labor or slavery or hard work. And then he said, in the future, there will be machines that look like humans that can replace human hard labor. So this caught a lot of attention. And then it became a science. And then people took it seriously. And then in 1956, the first conference, Dartmouth conference, the famous conference held in Dartmouth, some pioneers in artificial intelligence were there, and then they coined the term artificial intelligence in 1956 at Dartmouth. And then from there onwards, different generations carried this flag, and then we at Imperial are very serious about this mission. Somehow develop robots one day to free all mankind from all dangerous hard work and free them from work environments that are hazardous, working with toxic materials and things like that. So the history started like human-looking robots, but none of these robots could walk outside the lab. For example, I mean, they were okay on the carpeted floor or calibrated environments, but the moment they go outside, they fall. Nobody could understand why. I mean, we do things like we send rockets, we send we orbit satellites. We can have that control theory, very strong, precise control, but we cannot do this. I mean, it is across the globe. We are trying. We are missing something very subtle. So I will try to walk you through some of the secrets we think are very important as mechanical engineers to explore. So if you look at this fish, dead fish, it's a dead body, a dead fish in a fish in a tank. And then if I start a water flow against the body, and then if I speed up that water flow, after some time the dead body starts to swim. Right? Swim, not only swim against the water. Right? There's no brain there, it's just a dead body. So what it means is, there are circuits out there you cannot see. Part of the circuit is in the turbulence of the water. Part of the circuit is in the body, this musculoskeletal system. But when they are put together, they complete a circuit that can compute. And then that can generate propulsion forces that can do meaningful things, meaningful work, like moving the body or the fish against water. So these circuits are unseen. So we discount the power of these circuits, and then we believe that it is the brain always doing feedback control, and then we give full credit to the brain. But this is a classic example to show that it is not only the brain circuits that are working, it is the bodily circuits are also working to support intelligence. And then we just ignore that, and then we try to solve problems using pure control theory, and then we fail. No wonder. Right? So that is one. So you look at our own bodily parts, like ear. Right? So ear, before going to the brain, it has a funnel, it has a catchment area, and then it catches all the pressure signals, and then it funnels concentrated pressure waves to a drum that vibrates, and then there is a pure mechanical lever system that amplifies that signal. It is a bone circuit that amplifies the signal using lever theory. And then it sends to a cochlear tube. Along the cochlear tube, we have hair that can resonate at different frequencies. Right? So they have natural frequencies from 20 Hertz to 20,000 Hertz. And then if that particular frequency component is present in that liquid, cochlear liquid, it will resonate. And then each hair has a nervous signal, so nervous fiber going to the brain. So it's a parallel fiber stream going to the brain after having done a Fourier transform. So have you heard of that, like frequency analysis of signals? So the frequency analysis of the signal is done using pure mechanical circuits. And it is super fast because it's done in parallel computation, right? And then if you want to have a cochlear implant, all what they do is like implanting these things in the right places of the cochlea. And then if this liquid has more viscosity, you lose to hear. So when you grow old, so the mechanical circuit deteriorates, and then our hearing deteriorates. So don't discount the power of mechanical circuits and then their ability to do computation. Right? So if you miss them, we cannot achieve true level of intelligence, natural intelligence. As another example, so if you see these bugs, can somebody tell me how many motors do you think these bugs will have? Or how many sensors do they have? Any guesses? One sensor. How many motors? One motor. How many microprocessors they might be having? One. Actually none. So it is just a piece of rubber, right? So this is just a piece of rubber, no separated legs. It's just printed rubber. There's a vibrator here, and then the vibrator vibrates the whole body, and then those vibration signals bounce, make the body bounce off the ground. And if it didn't have these walls to bounce off, it wouldn't be doing any meaningful work. It will be just wandering away, right? So it needs the environment to guide it. So when you see cockroaches bouncing off walls and wall following, you might think that the cockroach's brain is doing an amazing thing in finding their way. They are not really doing anything amazingly complicated. They are just bouncing off sliding along walls. So it is just the body solving the problem rather than the brain doing it. They have a small brain, but they are central pattern generators. They just generate a sinusoidal waveform in the cockroach brain. So the environment also is very important. You take away this environment, these walls, these barriers, these bugs are not doing anything meaningful. Okay, so that is that. So in my view, there's nothing called a separate brain and a body. It's all the body and the brain making up a big circuit that solves problems. There's the only difference is the brain has higher plasticity in those circuits. Those circuits can really, very fast, they can reconfigure very fast. But the bodily circuits are slower to reconfigure, but they do reconfigure in the long run. Right? And then there can be cross communications between the bodily circuits and the brain circuits. We really don't understand today. But we move away from this conventional thought that there's a separate thing called a brain and a separate thing called a body, and the brain is trying to control the body. It is not true. It is the brain and the body working together to solve problems. So I'll show you some of the evidence we have gathered in the recent past through our experiments in this regard. So I talked about the hamster. So we wanted to see why we cannot hold a hamster. So we made our own hamster. This is a bicycle tire tube, and then we randomly inflate and deflate that tire tube using a computer program. And then we don't tell the robot, okay, so this is how we randomly inflate and deflate the robot. And then we ask the robot, okay, learn a strategy to hold this tube without dropping it. Right? It is like you, on a snowy day, you walk out and then you really don't know the friction coefficient of snow today or the ice today, but you just start to walk, and while walking you understand the snow, and then you learn and walk, right? So that is how it is. So what happened was here, if you ask the robot to not drop that tube, it will be very conservative and they will try to squeeze the tube and it will somehow drop it. So if you ask the robot in a different way, if you define the problem in a different way, saying, okay, if you feel that there's a risk of dropping that thing, try to squeeze it, but if you feel that there's no risk, just relax. So it is just looking at the risk of failing, not trying to hold it. And then it kept on holding it, and it didn't drop. So this is extremely important result for us. We published this in IEEE Transactional Robotics. You can download and read the mathematics going into it. For things like surgery. So in surgery, we need a robot to hold arteries while the other robot is doing some surgery, or cardiac surgery especially. When the tissue are pulsating, we have to do the surgery without stopping the heart. And then lung surgery, for example. So when lung tissue is really active, you have to do surgery, or abdominal palpation and things like that. So this mathematics is really important. So the key thing is probabilistic estimation of the risk of failing in the future, and then can you estimate when you will fail, and then if you can take action now to keep that failure point always in the future, you are never going to fail. That's the whole point. So it is not like waiting till the failure happens and taking a huge panic attack reaction, right? So it is about failure probability estimation. So extending this, I collaborate with Fumia, my colleague Fumia at Cambridge University, Etienne at Imperial, and Professor Simon Lusignan at Surrey Medical Center to develop a robotic phantom to solve a big problem we have, right? So elderly people mostly, they find it very hard to go to the hospital if they have a problem. And then if possible, we can send a robotic doctor to do a very basic examination at their home, like a general practitioner, GP level examination. We can screen patients and then send those people who really urgently need care to the hospital, and others can be treated at home. And then this need came even during the Ebola crisis, where Ebola patients in Africa were there, and then we had nurses and doctors who volunteered to go there, but it was too risky to go there. We were thinking of whether we can set a robot there to do a basic examination, and then do something, at least a very basic medical treatment from a different location. And then the other need is, like, so all your medical histories now are in documentation, right? So you go to the doctor writes your medical history. You go to another country, you completely lose that medical history. So we wanted to have a robotic patient that can archive your medical history so that a doctor can feel your history by touching the robot, right? So let's say 1 month ago, 2 months ago, how you felt like, right? So back and forth, going back and forth in the history is a good thing if you can do. So it's basically a robotic patient that can mimic you. So maybe you saw some of our phantoms in our demonstration. So the idea is this: a robot examining a patient in a remote location, and then another robotic phantom trying to replicate or camouflage the patient so that a doctor can examine the robotic phantom that is now trying to couple with the patient or trying to follow the patient, internal organ conditions. And then we, on the other hand, to develop this robot, we look at how doctors examine our abdomens, right? So if you carefully look at them, so they do various examination methods that require stiffness control of the fingers. Like sometimes they soften the fingers, sometimes they stiffen the fingers, they change the configuration. Why do they do that? That's a big question we have. So the hints were in this anatomy. So all our sensors or proprioception, like we feel force here in the tendon, we feel our movements in the spindles, but the spindles and the tendons are part of the muscles that we use for actuation. So you cannot feel without taking action. And then the good news is you can take action to control your perception, right? And then these are coupled intrinsically. And then if we understand this properly, we can make better robots that are safe to be sent near a patient. So that is exactly what we are doing in this project. So if you saw this, this is our Hogan. So this is rubber, but it really feels like a lever if you touched it upstairs. And then one of the PhD students, Liang He, is responsible for this innovation. And then we can create tumors, we can create different types of, let's say cirrhosis or swollen liver or cancer or various tumor types with just one organ, so that the doctor can really, we can present various conditions to medical students or doctors. So we have this technology now. And then we looked at a fundamental question: why, for example, we take action to feel? So if you give some 5-gram object to somebody and then a 200-gram to somebody, the same person, so the way they try to feel that object is try to bob it up and down. And then the way they bob it up and down is different depending on the weight of the object. So that means there's an object task-driven behavior to feel, right? So if we understand this, we can really crack a big problem in robotics. So this is because our muscles have sensors, and then by taking action, we can take a lot of data, and then we can fit models. And then the brain find it easier to understand the environment that way. So we call it entropy reduction. If you are mechanical engineers, you might have heard of this uncertainty reduction. So we mathematically model it, and then we take human data, and then we take muscle EMG data, and then we take movement data, and we build mathematical models, probabilistic models, and then we ask the robot to follow human strategy. And then we collect robotic data, and then what we see is the robotic examination goes to about 97% accuracy in detection detecting a nodule inside the soft tissue, whereas the human accuracy is something around 85%. So this is one of those cases where we start from a human strategy and then ask a robot, and the robot performs better than the human. So it is. So this is for example, like in medicine, if you can go from 85% accuracy to about 97% accuracy, it's a big achievement in terms of patient care. It's good news for us. So all these things are published and it is available online. You can download it from my website, Thrishlab.org, lab website or PLOS ONE. And then with a collaboration with my Japanese colleagues in Ryusui University in Kyoto, we developed a fingertip that can feel like human fingertips. So the idea of that is like our fingertips have things called mechanoreceptors. So when we rub against something, these mechanoreceptors dance against each other, and then the brain catches that dance. And then what we did was we suspended magnetic particles and Hall sensors, and then we looked at how this magnetic particle and Hall sensor movement can encode different textures, and then we could separate very look-alike textures to very clearly different textures. So these are really important for texture classification during medical examinations and surgery. And then even in other security applications. So Nicholas and Perla developed a more advanced finger that has that kind of mechanoreceptors, but in low resolution, and then a tendon sensor, and then a full controller that can control the stiffness of the finger, just like a human finger. So so far, this is the known, I would say, the most advanced finger, robotic finger available, and we are proud of making that. And then this will really contribute and change the way medicine is done in the future, or personal robots are developed in the future that can feel and touch. So one of my PhD students, Hasita, so he looked at not only the human fingertips, but also rats who really depend on whiskers. They use a similar strategy. So in the rat whisker, they whisk because they are nocturnal animals and they don't depend on their vision. They purely depend on their whiskers. That is their eyes. So each whisker has a follicle. And the follicle has two nervous innervations, like superficial ribosal nerve and a deep ribosal nerve. And then in between there's a muscle, the ring muscle, and then that can contract and stiffen the whisker or relax the whisker. So we wanted to understand what they are doing by doing so. We made a robotic whisker that can control the stiffness, just like the rat follicle. And then I'm skipping over things, and then what we found was very surprising. We found that this is entropy reduction, which is the information gain, and then that information gain increases up to a certain level when you increase the speed of whisking, and then when you increase further, it drops. So you don't gain enough information at very high speeds or very low speeds. There's an optimum speed of whisking, and then which is about 15 to 20 hertz of whisking, which is exactly what the rats are doing. And then indentation is like how much the rat should press against the texture to feel better. We see that beyond about 3 millimeters of pressing, you don't gain enough information. So from 0 to 1 millimeter, there's a huge jump, and to 2 millimeters to 3 millimeters, beyond that, there's no point in pressing. So we understood this by doing pure robotic experiments. And then now we know how to develop robotic whiskers and fingertips that can help maybe for future robots to do disaster response operations quickly, and then locate trapped humans inside rubble by having rat-like robots that can go through rubble very fast. So that is one. And then another PhD student, Sarah, is interested in goat hoofs. So how do these goats survive in this kind of cliffs without slipping? So because there's no time for the brain to react if there's a slip occurring. So her suspicion was that the hoof is doing a mechanical computation, or there's a mechanical computer in the hoof that does super fast calculations and then automatic reactions without the brain's involvement at all. So see, these goats are relaxing on tree branches. So she made a robotic hoof, and then she hypothesized that the fetlock joints and the coffin joints and their interaction with the interdigital ligaments might form a mechanical circuit, just like the dead fish you saw. The dead fish and then the turbulence making a circuit. That circuit might be there in the hoof. And then what she found, she mathematically modeled it and then made predictions using simulations. I'm going to skip it, and then this is the final experiment. She rubbed it against different surfaces, and then she found that by having the best stiffness combination, she can increase the friction 300%. Just by having the right stiffness in the ligaments, you can increase the work you had to do to slip against something. The surface is the same. The surface didn't change. The friction coefficients didn't change. It is the pure dynamics that is enhancing this resistance to slip through vibration dynamics. So this is a great finding. And then recently, Boston Dynamics, the big robotics company in Boston. So they are doing similar experiments on locomotion. And then this is a recent video they have about robots doing acrobatic jumps. And then this is by far, this is an MIT spin-off company from the professor Mark Rybert started this company, and then now it has grown to be a very, very powerful company. And then Mark Rybert, the CEO, came to London at some point, and then he invited Sarah to come on stage to show the goat hoof because he really appreciates that work. So it is, in conclusion, what I would say is like, things are really rapidly changing today. MIT, our colleagues are really advancing frontiers of science on that front. And I'm really happy to say that we in London are also playing a big role. Universities like UCL, Imperial and King's, so there's a big robotics community now. We are proud to say that we are also equally making a contribution. Okay, I'll skip this given the time. So finally, what I wanted to conclude is, if you had a view that our brain is separate from the body, I'm just requesting you to relax that view. Have a more holistic view, saying that our body is also important as a brain. Our body is an extended computer that does computations that are useful. And then by having the wrong body, it is impossible to get that supercomputer to control, and we will never succeed that way. That is my conclusion. And then for students, I want to show that now the robotic sales are skyrocketing in the recent years, like 2016 to 17. You can see the service robots, number of service robots sold, more than 6 million now. So sales, these are sales. The robotic companies are now they are booming. The robotics industry is booming. So this is a good time to be a robotic scientist. If you ever dream of becoming a robotic scientist, don't ignore the value of mathematics and mechanics. So pay good attention to those teachers. Pure basic science is really, really important to solve very challenging questions in the future. So, but be confident that the world is moving